Hello and welcome back to Calculus 2. In this video, we will see how to use integrals to calculate arc length along a given curve. So the idea here is that we have some function f of x. Let's just draw some curve, f of x, and we wish to find the arc length along this curve. So let's fix an axis here. Let's say we have x equals a and x equals b, and we wish to find the length of the curve from a to b. Now, this is the distance along the curve of the function rather than the distance along a straight line. So if we could imagine here maybe taking a piece of string and just laying it out and lining it right up with the graph. If we take that piece of string and then move it and straighten it back out, it would be really a little bit longer than just the horizontal distance here. We're really interested in the length along the curve, not just the distance linearly straight between these 2 points. So how can we find this kind of a length? How can we find a distance along a curve? Well, it turns out that we can find it using an integral. Let's call this length L. Let's just say that the length from when x equals a to when x equals b, the length of this curve is L. And we're going to take a small length along the curve. We're going to think of chopping up this curve into smaller portions. So let's just take a small portion of the curve right here. So this is a small slice of the curve. And we're thinking back to our idea that to find an entire expression, we want to just find a small slice of what we're interested in, and then we can integrate to get the total value. So in this case, we'll take a small slice of the curve, we'll find the distance of that slice along the curve, and then to find the total length, we will integrate. So let's call this slice of the curve dl. That's just this portion of curve. And the length along that portion we'll call dl. So the total length of the curve is just the integral of these representative lengths. We're adding up all of the representative lengths. So we integrate dl. Now this needs to be a definite integral. So we integrate dl, but what are the limits of integration here? What do we integrate to and from? Well, if we're integrating with respect to x, we'd integrate from a to b. Those would be the limits of integration. And we'll see a case where we can do that. However, there's also a scenario where we can integrate from two different y values. So we'll just leave off the limits of integration here, and we'll just think of the length as being the integral of dl. Again, the integral is adding up all of these representative slices of curve. Now, this expression is not very workable. There's not really anything we can do with this. What we want is an expression for dl in terms of x or in terms of y. So let's talk about how to get that. Imagine zooming in on this portion of the curve. Let's think of expanding that out and think of what we get there. So we're taking this portion of the curve, we're zooming in, it looks maybe something like this. And our slice now is right here. So we're slicing up thin enough, even though the curve might have some curvature to it like this, we're slicing up thin enough that that little bit of curvature doesn't matter. And really, we can approximate this length as being a perfectly straight line if we slice thin enough. So this is dl. And this is measured along the curve. This is a slanted distance. Now there is some horizontal component here. So let's imagine a horizontal component. And then there's some vertical component as well. So we're imagining a right triangle here. The horizontal component is some small change in x. Let's call that dx. The vertical component is some small change in y. What do we call that? We'll call that dy. So thinking of this small slice along the curve, there is a horizontal x component and a horizontal y component. Now, this is a right triangle, and we can relate these values using the Pythagorean theorem. So dl squared is dx squared plus dy squared, or we could write dl equals the square root of dx squared plus dy squared. We're using the Pythagorean theorem here. Now, let me just mention that this is a little bit hand-wavy. We could be more precise if we used delta L and delta X, delta Y, created a Riemann sum, and then found a limit to develop an integral. We're doing this a little bit more intuitively. We're kind of glossing over some of the details, but if we have an intuitive understanding of how this works, that's the main goal here. So we get this expression for dl. Now, we're going to manipulate this a little bit so that we can have something that's a little bit more workable. And at first this might seem a little bit strange, but I think as we continue, it'll make sense why we do these next couple steps. Now I'm going to divide and multiply by the same expression. I'm going to divide by dx and then multiply by dx. So really, I'm just multiplying by a strange form of 1, dx divided by dx. Again, this seems a little bit strange, but bear with me, and we'll see why this is used. Now, I can take the 1 over dx into the square root as long as I square it. Right now, it's outside the square root. I can bring it into the square root if I square the 1 over dx. So I can write this as the square root dx squared plus dy squared, all of that times 1 over dx squared. I've brought that 1 over dx into the square root, and in order to do that, I had to square it. And outside, I'm still just left with the dx that I had from the previous line. Now, distribute this 1 over dx squared into both of these terms under the square root. We have dx squared divided by dx squared plus dy squared divided by dx squared. So I'm just distributing the 1 over dx squared into both these terms. And again, we have the dx at the end. Now, dx squared over dx squared, this is just 1. So I have the square root of 1. And then dy squared over dx squared, I can think of this as dy over dx, that derivative, squared. So I will write that as dy over dx squared dx. This is an alternative expression for dl. And now we can recognize how we have an integrand here. We're integrating with respect to x if we use this expression. So this is one valid form of this expression for the length along the curve of a tiny slice, for this dl. So one expression for dl is the square root of 1 plus dy over dx squared dx. Now the dy over dx, this is literally just the derivative of the function. If we're writing the function as f of x, we could have just written this as f prime of x. But thinking in terms of dy over dx gives us a little bit more flexibility. The steps that we did to find dl in terms of dx could have been done the same way if we used dy instead of dx. So if we imagine multiplying and dividing by dy, we could get a similar expression. And if we do that, we'll not work through all the steps, but if we do that, we get a second valid expression for dy. It's the square root of 1 plus dx over dy, quantity squared, dy. So we have two valid expressions for this dl. And when we set up one of these integrals to compute arc length, we're going to choose using one or other of these expressions for dl. One of them we integrate with respect to x, the other we integrate with respect to y. If we choose the first expression, then the limits of integration will need to be x values. If we choose the second expression for dl, limits of integration will need to be y values. So we can use either expression for dl depending on which variable is simply more convenient. However, when we do this, we have to be careful that the limits of integration match the variable. So if we're using the dy expression and integrating with respect to y, we have to make sure that the limits of integration are y values to give the curve. Here's another way that we can think about this. If we imagine some curve y equals f of x, or if we imagine solving for x to get x as a function of y, and if this curve has a couple points, then we can find arc length between these 2 points 2 different ways. Let's draw a picture here so we understand what this is describing. We have some function f of x, and we're picking 2 points. This is the point a comma c. This is the point b comma d. We could find the length of this curve along the arc in 2 different ways. We could integrate with respect to x, and to do that we would have to find the derivative of y with respect to x. The limits of integration would be the x values a and b. Or we could solve this equation for y, and we could write this graph as x equals g of y, some function of y. Then we could take the derivative, which would be the derivative of x with respect to y, integrate with respect to y, and the limits of integration would be the y values of these points. Both of these integrals give us the same arc length. These integrals are equal, even though they use different variables and different limits of integration. There's different ways that we can arrive at the same arc length expression. Let's try some examples where we apply these arc length formulas. First of all, take a look at example 1. We want to set up and solve two integrals, one integrating with respect to x, the other with respect to y, to compute the arc length along the curve of y equals 2x plus 1 between x equals 2 and x equals 3. So first of all, let's write down our expression for the arc length along a curve. We have L equals the integral of dl, and we know that this is ultimately going to be a definite integral, but we don't know the limits here. And we're going to take two different directions. First, we'll see how to integrate with respect to x. And then secondly, we'll integrate with respect to y. So if we integrate with respect to x, we are going to use the following expression for dl. dl is the square root of 1 plus the derivative of y with respect to x, that quantity squared, and then integrating with respect to x. When we integrate with respect to y, we use a different value for dl. The value when we integrate with respect to y is 1 plus dx over dy quantity squared, all under the square root, integrating with respect to y. Now, if we integrate with respect to x, we have y equals 2x plus 1, and we're going to have the limits of integration x equals 2 and x equals 3. Now, if y equals 2x plus 1, then dy dx is the derivative of this function with respect to x. That's simply 2. So in this case, the arc length is the integral of dl, and we're using, once again, this expression for dl. So we have the integral from a to b, which would be from 2 to 3, using those x values. The square root of 1 plus dy dx squared. dy dx was 2, so we square that, integrating with respect to x. Now, let's contrast that with the integral with respect to y. When we integrate with respect to y, we need to find the derivative of x with respect to y. In order to find that, we have to solve the original equation for x. So we have y equals 2x plus 1. We want to solve this for x. We'd have y minus 1 equals 2x. So x equals y minus 1 divided by 2. That is the integral. That is the expression for x in terms of y. Also, we need y values for the limits of integration. We can get the y values that correspond to these x values by plugging the x values into the original function. So if x equals 2, then y will be 2 times 2 plus 1. So y equals 2 times 2 is 4, plus 1 is 5. Also, if x equals 3, then y equals 2 times 3 plus 1. 2 times 3 is 6, plus 1, we get 7 for y. So these will be the appropriate limits of integration for the y integral. All right, we have the expression for x in terms of y. We know what the limits of integration will be. Now we need to find dx dy. And I think it will help a little bit just to clarify things if we write x as 1/2 times y minus 1. So when we find dx dy, that will be the derivative of 1/2 times y minus 1 with respect to y. Well, 1/2 is a constant, so we can just take that out front. The derivative of y is 1, so we have 1/2 times 1. That is the derivative of y minus 1 over 2 with respect to y. So we have our expression for dx over dy. We have the limits of integration. Now we can write the final integral. Arc length is the integral from y equals 5 to y equals 7, square root of 1 plus dx over dy quantity squared. So we'll have 1/2 squared, and we're integrating with respect to y. Now, both of these integrals are expressing the same arc length. And we'll go ahead and solve them, and we'll find that we get the same value for each of the integrals. They're both measuring the same arc length. There's an integral with respect to x, there's an integral with respect to y. It doesn't really matter which one we use, they both will solve the problem. So first of all, let's integrate this first one. So we have the integral from 2 to 3. I'm going to square the 2, we get 4. 1 plus 4 is 5, so I'm integrating the square root of 5. That's simply a constant. The integral of a constant is the constant times x from 2 to 3. So first we input 3, square root of 5 times 3. Then we input a 2, minus square root of 5 times 2. We have 3 square roots of 5 minus 2 square roots of 5. The final answer here is 1 square root of 5. So this is the arc length of the curve. Let's solve the second integral, and we'll notice that we get exactly the same thing. So we have the integral from 5 to 7. We'll square the 1/2. That's 1 plus 1/4. If we square the 1, we get 1. If we square the 2, we get 4. So we have 1 plus 1/4. We want common denominators here. I'll just do some scratch work off to the side. We have 1, which is 4 over 4, plus 1 over 4. This is 5 over 4. That's all inside the square root, and we're integrating with respect to y. So we have the integral from 5 to 7, the square root of 5 over 4, dy. Once again, we have just a constant, so the antiderivative of the constant is the constant times the variable, which is y. So we have square root of 5/4 times y from 5 to 7. We'll input a 7, we'll input a 5, and then we'll get the final answers. Square root of 5/4 times 7 minus square root of 5/4 times 5. We have 7 times the square root minus 5 times the square root. The difference here would be 2 times the square root. So we have 2 times the square root of 5 over 4. We can split up the fraction with the square root. We can write this as 2 times the square root of 5 divided by the square root of 4. The square root of 4 is simply 2, so these 2's would cancel, and once again we have the square root of 5. Notice that we get the same answer from both integrals because they are both describing the same arc length. Now let's return to the original problem statement and see if we can understand this a little bit better, perhaps more intuitively. So we solved the problem. We found that the answer here is square root of 5. But can we think of the context? We have the function y equals 2x plus 1. That's just a linear function. We can graph that. It has a y-intercept of 1, and it has a slope of 2. So it would look something like this. Here's the graph y equals 2x plus 1. And we're going from x equals 2 to x equals 3. We found that the y values of these points are 5 and 7. And we're finding this length along the curve. Now this is just a straight line, and we can imagine creating a triangle here, just like this. The difference between the x points here, this difference is 1. So this side length of the triangle is 1. The difference between the y coordinates is a difference of 2. So the height of the triangle is 2, and we have a right triangle. The way to get the length of the hypotenuse is to use the Pythagorean theorem. So we get the length of the hypotenuse. This is our value L. It equals the square root of 1 squared plus 2 squared. 1 squared is 1. 2 squared is 4. We have the square root of 1 plus 4, square root of 5. We get the same expression. So you might think, well, why did we go through all the work of integrating and doing two different integrals if we could have just found the length using the Pythagorean theorem? Well, for this problem, Pythagorean theorem works because we just have a line. But for the next several problems, we do not have just straight lines, so the only way to find the arc length will be to use our integral formulas.